In the immediately preceding examples, we were looking at time series which were not stationary because they had trends present. In particular, trends that we were able to eliminate by first differencing, possibly first differencing multiple times. There's another way that time series can be non-stationary, and that is that the variance, or even any part of the variance covariance, can be not the same throughout time. So time series can be stationary for reasons other than trend. For instance, the figure we're about to look at shows data which exhibit a trend, but it also shows another kind of non-stationarity, the fact that the variance changes over time. That kind of behavior is called heteroskedasticity. And it often happens that the variance of the data is larger when the data itself is larger, as is the case for this example. When that happens, we can sometimes eliminate the heteroskedasticity by transforming the data. And a common approach is to log transform the data. We just compute the logarithm of each data value. When I apply that to these data, it gives this. And it turns out that by that process, the heteroskedasticity has been eliminated. And we still have a trend present, however, but that can be eliminated by first differencing. As in the following figure, the first differenced log transformed data are, in fact, a stationary time series. Sometimes log transforming doesn't do the trick. It doesn't eliminate heteroskedasticity, it just changes it. For example, let's take a look at the time series of monthly mean sunspot numbers since January 1900. If you look closely, you can probably see that the variance, the amount of variation that happens, tends to be bigger when the sunspot count is higher and tends to be less when the sunspot count is lower. If, however, I compute the logarithm of the sunspot counts, I'll get a transformed time series, but it won't solve the problem, it'll just reverse it. So what happens is that there's greater variance when sunspot counts are low than when they're high. Well, if log transforming doesn't do the trick, because there's some way we can essentially eliminate the time changes of variance, the heteroskedasticity, there is a common strategy, and that's to subject the data to a power transform. What we essentially do is raise the data values to some power. Often we will then transform that for friendly reasons. For instance, a common way is to take the data, raise it to some well-chosen exponent lambda, subtract 1, and then divide by this quantity in the denominator, and the quantity g is the geometric mean of the x values. Now, the reason that all that extra stuff is done after raising the original data to some exponent lambda is that we want the units of measurement to remain unchanged. If we're working in sunspot counts, we wouldn't want to work in squared sunspot counts or square root counts, but in just counts. Sometimes that's important, but usually it's not really that critical. So sometimes that g factor is ignored, and that gives us a very similar transform, which is called the Box-Cox transform. Just raise it to some exponent, lambda, subtract 1, and divide by the exponent. When we use this definition, the log transform of the data is what we get from taking the limit of the Box-Cox transform as the exponent lambda approaches 0. Now, the following graph is going to show the result of applying a Box-Cox transform to sunspot counts with exponent equal to 1/2. Well, when we do that, and here I haven't bothered even subtracting 1 and divided by lambda, I just took the square root of sunspot counts. And when I do, I have eliminated the heteroskedasticity, at least as far as the data show. When I test this for heteroskedasticity, the tests indicate that there's no real evidence of that. So we started with a time series which was not stationary, it still isn't, but it also showed heteroskedasticity, different variance at different times. But by a square root transform, I was able to remove that property and create a time series which has about the same amount of variance at all times.